Independent and dependent probability. So Sam has a bag containing 15 Skittles. There are 4 red, 3 green, 5 yellow, and 3 orange. What is the probability you shake the bag and out comes a red Skittle? Well, theoretically here we have 4 red out of 15. So that would be our probability of actually getting one. Okay. Now suppose you shake, okay, so now we're going back to the beginning. Our full bag is 15 Skittles, okay? Now suppose you shake the bag and out comes a yellow Skittle. What would now be the probability that you got a red Skittle? So what is the probability that you get a red Skittle given that you received a yellow one prior? This line means given that. What is the probability you receive a red Skittle given that you just got a yellow? Well, then if you just got a yellow, there's only 14 Skittles, and that would be a 4 out of 14. Okay. Notice that in our second example, the probability of receiving a red Skittle depended on the event of receiving a yellow. So independent and dependent probabilities. Probabilities where they depend on one another or not. It says decide whether the following events are independent or dependent. If I roll a die and I toss a coin, does my number on the die affect the coin toss? No, those are independent probabilities. Okay. I take a marble out of a bag. Nothing affected that. But then I take a second marble out of the bag. Oh, it is dependent on what I got in that first pull. I choose a person from a group of 50 people. Nothing was affecting that. And then I choose another person from that same group. Well, whatever person I picked, it's going to affect the next probability. I draw a card from a deck. Well, I didn't put it back, so I draw a card again from the same deck. I don't have 52, I now have 51. Okay. Oh, I put it back. I'm sorry. That would be if you didn't put it back. If you put it back, it's like you reset, and so the next card would be independent because you go from 52 cards to 52 cards. Okay. So here's a toy box. Some of the toys faded on the box. That's a star. This is an umbrella. Is that even anything? We'll just go with that. Okay. So here's a toy box. There's a star, a starfish, a puzzle piece, a tree, a heart, and an umbrella. What is the probability that you get a heart and then you get a tree and then you get an umbrella? Well, you'd write it like this when you're in middle school, but really what this is saying, what's the probability you get a heart? What's the probability given a tree given that you just got a heart? And what's the probability given an umbrella given that you just got a tree given that you just got a heart? So what's the probability you get a heart? That's a 1 out of 6 times, because fundamental counting principle, you do something, then you do something, then you do something. You multiply those ways together. So what's the probability you get a heart is 1/6. The probability you then get a tree is 1 out of 5 since you just got a heart. And what's the probability you get a umbrella? I don't know why I said it like that. 1 out of 4. So that'd be 1 out of 120. Okay, so we tend to write as fractions, but I like writing them as percents as well because our mind can conceptualize what 1 divided by 120 is, and that is 0.0083 repeating, or 0.83%. When we see it as percents, we're like, oh, wow, that is really small. Okay, the next one. Find all the probabilities, assume you do put the objects back. So what's the probability you get a heart, you get a tree, and you get a umbrella? If you put them back, it doesn't matter. It's reset. So the probability a heart is 1 out of 6, a tree is 1 out of 6, and an umbrella is a 1 out of 6. You've made a smaller probability because when you put the objects back, you have more to choose out of. So it's going to be 1 out of 216, so it's going to be a lower probability, which is about 0.46%. What if none of the objects are hearts? Well, 1, 2, 3, 4, 5. None of the objects are heart. That's 5 out of 6. Okay. I wrote this little C here because that means the complement. It means not a heart. Okay. Here, it says if A and B are independent events, you just multiply your ways together. If they're dependent events, like they affect each other, what's the probability of A times the probability of B given that A just happened? That's how you write it. Okay. Here it says Lee has 18 black socks and 12 white socks. Every morning he chooses one sock at random. After he pulled that one sock out, he chooses another sock at random and wears them. What's the probability that he pulls a white sock and then a white sock given that he just got a white? Well, that's 12 white socks out of 30. And then since he just pulled a white sock, it's out of 29 now and out of 11 because he just pulled a white. Okay, when we multiply those together, 30 times 29 is 870. And 12 times 11 is 132, which is, when you put in the calculator, that's about 15%. What's the probability you get a black sock and then you get another black sock given that you just got a black sock? So since they depend on each other, we write it like this. So the probability you have a black sock is 18 out of 30. Since you just got a black sock, now you're left with 17. And since you just pulled one sock, that's one less in the drawer. So it's still going to be out of 870. But now it's 18 times 17. 306. That is about 35%. Okay. What's the probability you got a white sock and then a black sock? Well, since the white sock affected the black sock, it's written like this. So the probability you got a white sock was 12 out of 30. What's the probability you have a black sock? Given that you just got a white, that means there's one less sock in the drawer, but there is 18 black. So that's 870. 12 times 18 is 216 divided by 870. That is about 25%. Well, what if it's the other way around? What if it's a black sock and then a white sock given a black sock? Well, it shouldn't matter, right? 18 black out of 30 were one less sock in the drawer. White socks are 12. You're going to get 216 out of 870. So that's 25%. So let's think about this. We did a white and a white, a black and a black, a white, black, a black, white. Those are all the percents. 25, 50, 85, 100. You should get 100% for all of your sample space. It says, therefore, what is the probability he gets a pair? So a pair would be probability of getting a white and then a white, or the probability of getting a black and then a black. Of course, we should be writing this as given that you just got a black. So or is more, the white and white is 15%, plus the probability of being black is 35%. So that's 50% chance you get a pair, a matching pair. What if you get a mismatch? That's a white and a black, or a black and a white. So that's 25% and 25%, which is 50% as well. Well, that makes sense. Those are your only options. So that is independent and dependent probabilities. Complete these notes and submit.